So hello, I'm going to explain how to fit a second order critically damped model to the step response of a system. My name is David Castillo, and well, let's begin. First of all, the second order system is the lowest order system capable of an oscillatory response to a step input. Typical examples are the spring mass damper system, which is going to be our example in this video today, and the electronic RLC circuit, which is an electrical circuit consisting of a resistor, an inductor, and a capacitor that are connected in series or in parallel. The circuit forms a harmonic oscillator for current and resonates in a similar way as an LC circuit. So from this we can obtain the information that in second order systems an oscillatory behavior is pretty common, or actually it is always present. For example, here we have the three options in a second order system, which can be the underdamped, here, which typically its behavior is, well, we have a lot of oscillation, as we can see here. We have also the critically damped, which is going to be the one we are going to work with here, and the overdamped, which the main difference between these two are that the overdamp is a little slower and critically damped is a little faster in order to get the final value. Then moving on, we have our standard form for the second order system, where K is the gain, tau is the natural period of oscillation of our system, and zeta is the damping factor or damping ratio. And well, here we have that this final value is has to be 1 for the standard form. So we have to keep that in mind, because if this wasn't 1, this will become Wn, which is the natural frequency. But in order to have our standard form, we will have to divide both sides for equally for this value of the natural frequency in order to get our standard form. And so we also, here we have the corresponding differential equation for this standard form. And next, we have the characteristic equation, which is the denominator of our standard form here. And it is a characteristic equation because from analyzing this denominator, we can get the stability and behavior of the system just by looking at the roots of this equation. And we can get a pretty good first glance of what will we have. For example, if we get the roots of zeta by obtaining the general equation, the general quadratic equation, if zeta is bigger than 1, we get an overdamped with 2 distinct real roots. If zeta is equal to 1, we have the critically damped, which is 2 equal real roots. And if we get a zeta between 0 and 1, we have an underdamped with 2 complex conjugate roots. And basically what we will get is what we saw in the first slide, which is going to be like this something. Critically damped and over damped, and like I said, it will be like something more straight than the critically damped, and it will take for it longer to reach the final value. And the underdamped, well, we will have a lot of oscillations before reaching our final value. So now we will have before we move into our example, the second order system can be present in cases like, for example, we have multiple capacity systems in series, like, for example, two first order systems together, like we saw in class, two tanks in series, or from oscillatory systems. And like I said, and here we have our example, which is the spring mass damper system, where here we have our spring damp system and our mass. And from this, what we have is the force exerted by the spring, which is going to be K times the the X, which is going to be not the height, but how long, yeah, it will deform. And then we have the force exerted by the damper. And from this, and the force exerted by the inertia of the mass. So we can see from here that we have 1, 2, 3, and 4 variables. Well, F, which is equal to the force. Then we have from here we have our equation, which describes the entire system. Whenever in this example, with our finger, we push the mass towards the wall, and then we release it. And applying Laplace transform, we get the next equation. And from here, we get our transfer function up next, which then, well, here you can see the characteristic equation, which is the denominator of the transfer function. Here we have a more accurate representation of this transfer function that we have, of how it can describe our system, our spring damp system. So now let's imagine we have this this response. So we are going to analyze this. So first we have to get our values, and our model, obviously, which is going to be the next one. Here you can see. From here, we get our step will be of equal 1 to 1. And we know from also our model that we can get the value of tau, where it is the percentage equal of 26.425 of the final value of y, which is going to be, in this case, the the 10 meters, which is going to be the final value of our spring. So we have here YF equal to 10. From our final value and our step, we can get the gain from this equation. So we get that it is equal to 10. And tau, we multiply our values. We get that it is equal to 2.6425 seconds. Finally, we can write our fitted model by expanding our polynomial and putting our values that we got. So k is equal to 10. Then we have that this has to be the square of tau times s, square of s, which is going to be 6.9828. And then we have the next term, which is going to be 2 times, well, a times b, which is going to be 5.285 seconds. No, sorry, 5.285 s. And well, our last term, which is going to be a square of 1, which is going to be 1. So this is our fitted model. And from this fitted model, we can get our values of our system that we have from this explanation. So we can get the mass and the values of the damp and the spring system. So we can get somewhat of a response, somewhat of an idea of what these systems, of what this system is made of. Okay, so from our values, from here, from our fitted model, we get, well, we have to get the same values for our system. So we divide everything by 10 to get our 1 on top, and being equal in top and bottom. So we divide everything by 10 and we get our values. Our mass will be of 0.6828. The value of the damp system will be of 0.5285. And the value of our spring, K, will be equal to 0.1. Finally, with help of Simulink, I graphed our fitted model this way in order to see what we will get. What we expect would be an equal behavior like this graph, which is critically damped. And so that was actually what we got. Here we can see how the final value has to be 10, which it is. And it reaches this final value around the 22.5 seconds. So we can we can say that this was a successful example of how a critically damped system can be fitted into a spring damped mass system. And thank you for your time.